So I'm not sure what's going to happen now because probably can need not read my laptop screen and not read the blackboard. I can do without. I can do without power. I'll look for that afterwards. I think it's alright. Okay, so I'll start with just doing 2 more slides of the last session because they're relevant for the practical work, and then I will continue with the last lecture. So you all started, or most of you are close to finishing, are finished with coding up the wave equation, and to keep things simple, we are using periodic boundary conditions. But of course, for many purposes, periodic boundary conditions are not what you really need. Well, it looks like I don't need that. Because otherwise I have to stand in front of it and you can't see anything. So we talked a lot about these characteristic fields, these characteristic variables, right? The variables, the linear combination of variables. This looks kind of funny. Which propagate with a particular speed. And so now these are also very relevant for putting boundary conditions, because you can easily see that putting boundary conditions on the outgoing characteristic fields is not logically consistent. And for that also, the initial boundary value problem will not be well posed. Why is this? Because if there's some information traveling out of the computational domain, we can't put a boundary condition on that. It's just coming to the boundary from the inside. We can only put a boundary condition in what is coming into the computational domain, right? So only on the characteristics which are traveling inward, we can actually put boundary conditions. 2 standard examples of boundary conditions that are also easy to derive are, the first thing is also usually not in our context, not so physically important, reflecting boundary conditions. For those, what you want to do is you just keep your scalar field phi constant on the boundary. If that's constant on the boundary, what it has to be, the usual thing is that we just put it 0 on the boundary, but if that's 0, then its time derivative has also to be 0, which means that its variable pi has to be 0. But if that's 0, its time derivative also has to be 0, which means that from the evolution equation we can convert pi dot to the spatial derivative of this variable x, so this also has to be 0. Okay? So now you have to, the freedom in implementing this now is how to discretize this derivative close to the boundary, and the most simple thing, which is just first order accurate, but it's going to work, is that basically you just set psi n, let's say, the value of psi at the outermost grid point to psi n minus 1, the previous one. Because if they're the same, then the first order, that just has the consequence that the derivative is 0, right? And so that implements this boundary condition. Usually what we're thinking of is outgoing boundary condition, which means that we have some computational domain, there's some kind of radiation, and asymptotically this radiation just moves outward and leaves the computational domain. So what does mean outgoing boundary conditions? That we just set the incoming signal to 0. So for example, at the left boundary where we wrote this characteristic variables, right? This is the right moving one, so this is what we set to 0 at the left boundary. That was just 1/2 pi minus psi, so this means pi minus psi has to be 0, which means that pi is equal to psi. Okay, so just you have to set one of those in terms of the other. Okay, and you can easily derive what is the analogous condition at the right boundary. Okay, so now this is what you're missing to do some more physically realistic simulations of a scalar field. Well, physically realistic, just make this toy model look more like what we want to achieve in the end. And then the next step would be, and I just give you here the equations, and hopefully there's enough time to look into this a little bit more and code it up next week.
Can you repeat the outgoing boundary condition?
Sure. So outgoing boundary condition means that there is no incoming radiation, that everything goes out, right? And so, for example, we are at the left boundary, So we set that characteristic field, which corresponds to motion toward the right, to 0. And this is what this we looked at it before, right? It was this combination. And so it means pi minus psi has to be 0. So we just have to set pi is equal to psi, right? That's what we have to do. And then, so if you want to couple the scalar field to gravity, well, we'll just look at this in, oops, I see I have lost some equation up there, but actually, why don't we fix that? Oops. Well, not so easy actually. I think that. All right. So now, just for simplicity, we will only do this in spherical symmetry. What physics are we losing when we go to spherical symmetry? Well, mostly we lose gravitational waves. Right? There are no gravitational waves in spherical symmetry because of the Birkhoff theorem and many other things, of course. And so, in some sense, this is the simplest model, which kind of looks a lot like a star or some compact system which gives off radiation, except that our radiation is not gravitational radiation, but it's scalar field radiation. Now, what we have to decide is how we write, what ansatz we make, how we write the spherical metric. There are different ways, and one useful simple form is this one here. You see that there's no shift vector, right? And there are just two metric variables which are non-trivial, which we have to solve for. One is alpha. We call it alpha. You know what it is? It's the lapse function, right? And then there's another one, the radial metric component, and we just call this free function A. And why is this metric, this particular ansatz, so simple? Well, because you see that here we have r squared times the standard line element on the surface of the sphere. So we have chosen an aerial radial coordinate, right? You're all familiar with that choice, and it makes things particularly simple. And it turns out to be we just do treat things very, very similar to the wave equation of flat space, except that now because we have this non-trivial metric component, it turns out that for the psi and pi definitions we had before, we changed them slightly. We changed the definition of pi just a little bit with this extra factor. Then we insert all of these ansatz into the Einstein equations. We get three equations. We see that there are two radial equations, and one here which has a time dependence. But the overall equations are, of course, second order in time. So in some sense, all of these play a role like constraint equations. In fact, this is the Hamiltonian constraint. This is the momentum constraint. This is one of the other Einstein equations. But because we have chosen this very simple setup, it actually just is a radial equation. So this means this is very nice because all the Einstein, so what we can actually do now, because we just have two variables for the metric alpha and A, we just need two equations for them. And we could, for example, just eliminate this one and just use these equations to construct the metric. This is what is called constrained evolution. We don't actually need an evolution equation for the metric. Okay? We just have this radial, or you see that these are ordinary differential equations in the radius. So this means that every time we construct the metric components alpha and A from these radial ordinary differential equations. Right? And here they do couple to the matter, of course. So this is something like the energy density, and this is how this matter field influences the construction of the metric components. Of course, what we do need also is the equations for the scalar field, and this is just now the wave equation on this curved background, and we get three equations. Phi is just the definition of pi, essentially, and we get two non-trivial evolution equations for pi and psi, and you can easily see that if alpha and A are 1, then this is just the standard radial wave equation on flat space. Okay, this is just one way of writing the radial part of the Laplace operator. Okay, so in principle, it's straightforward to just modify your, for example, if you want to just do a scalar field on a given curved background, you could just solve these equations here for given functions alpha and A, and you essentially just have the code, basically you have the code ready for that, okay? You have your method of lines code ready to solve this problem, and if you want to couple it to the Einstein equations, if you want to see how the metric changes due to the effect of the evolving scalar field, then at every time step you also have to solve these two radial ordinary differential equations. But it's a relatively simple problem, and you're basically ready to deal with that. All right. So this was all I wanted to say about finishing simple examples of the wave equation. And now we will start with the last lecture. Oops. And in the last lecture, we'll just try to, in a very compressed form, talk about some of the topics that we left out. Okay. Yeah. Since I have to take over for Thomas, I wasn't able to completely prepare the talk. That was going to be a Google picture from Monty Python, but didn't have time for that. The first topic that we'll talk about is to capture radiation, and in order to do that, we have to talk a little bit about infinite computational domains. So let's look at this a little bit. And this will be really much less detail now, but I think it's important to give you a little bit of an idea of what happens when we actually treat astrophysical systems with the Einstein equations. All right. So in astrophysics, what we want to do is, for astrophysical processes, as opposed to, for example, cosmology, okay, there are kind of two key concepts which are important. One is that whatever happens, it's essentially independent of the large-scale structure of the universe. And the second is that, radiation can leave the system. Electromagnetic radiation, but of course also gravitational waves. And if you want to idealize this physically, then we can call such systems an isolated system. And the basic idea is, from the point of view of general relativity, that the geometry, the metric, just flattens out if you go far away from where the matter is. So the geometry has to approach Minkowski space if you just go far away from a star or a galaxy or black hole. Okay? Or in some sense, we can also think that just approaches some cosmological background geometry, just far away. Okay. There's another, so far so good, but there's a complication that I think you're well aware of, that in general relativity, you cannot define a local energy density, and that's basically because of the equivalence principle. Okay, because the equivalence principle means accelerated frame cannot be distinguished from the effect of the gravitational field locally. So you cannot define a local energy density of the gravitational field, because locally it just doesn't have a meaning, right? There's a number of subtleties associated with this, but that's the basic idea. And so therefore, certain quantities, which are somehow the very basis of our physical understanding, in the presence of a general gravitational field, in the presence of gravitational waves, we cannot define them. So things like mass, momentum, or what's the amount of emitted gravitational wave energy, they cannot be defined unambiguously in some local or quasi-local way, right? So in GR, we cannot rigorously define what's the amount of energy in this room, okay? We can only do that in some asymptotic limits. So if we go infinitely far away from where the matter is, where the geometry approaches Minkowski space, then we can use this background structure of Minkowski space to define something like a total energy, and then we can make a definition of the rate of change of the total energy and compute how much energy is lost to gravitational waves. Okay? So this can be formalized, this idea of an isolated system, and this is what usually is called as an asymptotically flat or asymptotically de Sitter or asymptotically anti-de Sitter spacetime. Okay? For astrophysics, usually what we are interested in to consider asymptotically flat spacetimes. So these are usually the basis of models of sources of gravitational waves. Now, there's another complication, is that because it's relativity, if we go far away from our sources, we can do this along three different directions. Okay? We can do it along the time-like direction, which means just staying where we are forever. Okay? That means going to infinity along a time-like direction, or space-like, moving away to an infinite space-like direction, so that the proper distance just goes to infinity, or we can go away on a null direction, following a light ray to infinite distance. And of course, this is the most interesting one, because if we, as astronomers, observers, we observe astrophysical distance, astrophysical system through its photons or gravitational waves, then they came to us via null rays, right? So this is the direction which is the interesting one. Now, it turns out there's a very useful way of dealing with these problems technically, because we have to go to infinity and then do calculations in the limit of going to infinity. But in relativity, this is difficult because if you want to say we go to infinite value of the radius, this is like a coordinate-dependent statement. You would like to make these things in a coordinate-independent way. And there's a very nice idea. The key idea, which is due to Penrose, is to use conformal rescalings. In order to understand this, let's make this picture here a little bit bigger. What is a conformal rescaling? It is we take our physical metric, call it G physicals, that's our physical metric, and I just multiply that with a scalar function squared. I just choose square just to make sure that this is always positive, and it turns out that the power of 2 is just convenient. And so this defines a new metric, a rescaled metric, which I call the compactified metric, because what I do is I just let this, as the separation goes to infinity, I let this omega go to 0 in an appropriate way. Okay? So this makes things which have the metric describes the distance, right? So if I just multiply my metric with 0 as the coordinates go to infinity, that just pulls in infinity to a finite distance in this unphysical metric. Okay? I don't want to really go through the calculations, but if you look at an advanced textbook like Walt, you can easily find the explicit calculation, for example, for Minkowski spacetime or for Schwarzschild. It's not that hard, and just go through the calculation. What does it amount to? Right? You compute, you choose some appropriate factor omega here, which has the right property of going to 0. You compute your new metric, and then you want to somehow represent your metric. It's on a compact manifold, and you can embed your compact manifold into something larger, like again into Minkowski space or some cosmological space, and it has this nice structure where there's this this will be now that this is the compact manifold. Now it has a boundary, right? Let's say Minkowski space doesn't have a boundary. The boundary is infinity. It doesn't really part of the manifold. But now after the compactification, there's the interior, which is the finite part, and it has a boundary, which are the points at infinity. So now we have explicit access to them. And these points, there are different ones. So there's time-like infinity if we just go along a time-like curve. Right here we choose coordinates such that the speed of photons travel at 45 degrees. Time-like curves go like this. We can go to time-like infinity or space-like infinity like that. Or to null infinity. If we start here, we go to null infinity, we just go at 45 degrees. Right? That's the basic idea. And there are standard names for these things. We call future time-lag infinity, we call this I plus. Same thing for the past I minus. I0 this is space-like infinity, which we can somehow consider as a single point. And then null infinity, where the photons go, we should usually write this with this script I, or short for scry. So now, well, that's the basic idea. Okay, what it allows us to do is to work on this unphysical space-time, and then we can discuss this asymptotics, which means discuss statements about gravitational waves or the total energy in terms of local differential geometry, just working locally on this boundary, which we just showed in this picture. Let's just to make this clear, actually, why do we do this in this conformal way? We could just have done this compactification in different ways. We do it in this as a conformal rescaling, because conformal rescalings, they leave angles invariant, which means, let's say 45 degrees goes to 45 degrees, which means the light cone goes to the light cone. The light cone defines the causal structure, which is of course essential for understanding the manifold. So conformal rescalings of Lorentzian manifolds are those which leave the causal structure invariant. That's why they are useful and interesting. Okay. And then we can define the physical manifold here. I call this M tilde. This is just all those points in this artificial manifold M such that the conformal factor is positive, so non-zeros. This is like the interior. And then the infinity is this boundary where exactly those points where the conformal factor is 0. Okay, but there's some definitions. This may all sound very nice. So now what we can do is we can just insert this definition into the Einstein vacuum equations. Okay, I've chosen the standard mathematicians kind of convention here that tilde means it's physical, and no tilde means it's the compactified one. So now this is the physical metric. We just insert this into the Einstein equations, just work out what we get, and we get three terms. One is the Einstein tensor evaluated for the compact metric, so that. But then we get two more terms which are divisions by omega. So these terms are singular. Non-surprisingly, because we just have pulled infinity into a finite distance, so quite generally that makes the equation singular. We don't really want to discuss the effects of this singularity and how to remove it, how to deal with it. But what we can do is we can just multiply the whole equation with omega squared. If you do this with omega squared, then this term goes to 0. This is the Einstein tensor of a regular metric. It's finite, so that goes to 0. At omega goes to 0. This goes with 2 over omega, so that also goes to 0. And then this goes to 1 here. Right? So now what we have is that there's the physical quantity also goes to 0. So now we get that the gradient squared of this omega quantity goes to 0 at infinity, which means nothing else, that's a null vector, right? So we see that, so we have just derived that the structure of infinity in the asymptotically flat case is that it's a null surface because it's spanned by null vectors. Okay, the gradient of this omega is a null vector. It turns out that if we add here the cosmological constant, we have one more term, and the effect of that is that in the asymptotically de Sitter case, if you have a positive cosmological constant, the null infinity is space-like, so the infinity where photons go is space-like, and then in the anti-de Sitter case, which recently has also is attracting a lot of interest, then it's actually time-like. All right, let me just not go into these technical details because the main point is just, so now we have this basic picture that if you actually want to know what is the gravitational wave signal of some space encoded in a metric, we actually have to go to infinity. There's a nice formalism that uses conformal rescaling to do this in a precise way. Now, it is actually possible to, we just saw that the Einstein equations in this case become singular, and there are different ways of regularizing that and working directly on the compactified spacetime. It's also very complicated, and it's possible for, let's say, astrophysical calculations only with some restrictions. So now, what we usually do, if we, in some simulation of neutron stars or black holes, for example, is that we, there's a chalk. Right, what we would like to do, so we had just this picture, but at the moment it's a picture for you. This would be this, what is also called the Penrose diagram. So this is just a picture of the compactified space-time. We just have derived that this is null infinity. Right, this is where photons go. So here you have some source. For example, here you have some neutron star, some source, some binary. If this sends off photons or gravitational waves, they go here. Right? That's where you can think of, that's where an observer sits with his telescope observing things. If you consider an object which is at a finite separation, a finite radius, this would be a curve like this, for example, right? And if it's a so larger finite radius, let's say like that. If we, what would be this surface, for example, here? So this would be a surface of constant time, and we can easily see what is the future domain of dependence, right? Just to connect what we said before. Well, this is the future domain of dependence. This is the past domain of dependence because it just goes with a light cone. So in this case, we have that the whole manifold is the union of future and past domain of dependence. So it's a typical example of a globally hyperbolic spacetime. Okay. If this is Minkowski space, then we have this simple picture that we showed before. If it's Schwarzschild, for example, or there's a black hole, then at the end things become singular and cut off here with a singularity. Now, what we usually do in a calculation, we can only go with our computational grid when it can only go to some finite radius. Okay? To what kind of radius? Well, probably would be good to go into the wave regime further away than, let's say, the wavelength, up to one wavelength, up to two wavelengths or further. That would be good. Okay? And so, let's say we could try to read off approximately what our wave signal is at some large radius. But it would not be exact, because the exact thing is we have to really take the limit to infinity. So what's the practical thing that we do? It's exactly the same logic that we use when we want to understand whether our numerical solution gives the right answer. We do it for different resolutions, and we make a convergence test. So in this case, we say, we can't really go to infinity. Just compute a wave signal maybe for 3 resolutions or for more, so for 3 radii, and then just make a convergence test whether if we go further out, we converge to some answer with the expected rate. So that's what happens in practice. You compute the wave signal at some finite separation, and you just do it at several separations and try to see whether you get a reliable answer. Okay? Don't want to go somehow into details much more. How can we characterize the gravitational wave signal far away? Well, far away, we're in vacuum. We have the sources inside. Far out, we have vacuum. And we can characterize gravitational waves by the Weil tensor, certain components of the Weil tensor. Well, if it's vacuum, Weil tensor and Riemann tensor are the same. And it turns out that there's a particular component of the Riemann tensor in an appropriately adapted basis, which is usually called psi4, and it's this one particular component of the Riemann tensor that encodes the outgoing gravitational waves. Okay? It precisely corresponds to the outgoing gravitational waves if you're at infinity. At some finite radius, we're making some error, and that's why we look at this quantity at different radii. In fact, and I don't want to go into this in much detail, some of you will for sure will know that, the appropriate basis that we have to use here to project this component of the Riemann tensor is a complex one, and so this quantity psi4 is complex, which means it has 2 real degrees of freedom. And why is this? Well, as you know, the gravitational wave signal, like electromagnetic waves, has 2 polarization states, so there are 2 degrees of freedom, and it's very convenient to encode this in one complex number. So the recipe, therefore, in short, to compute the gravitational wave signal in a numerical spacetime, when you have computed your metric numerically, following Thomas's equations and the numerical methods we have discussed in this class, is try to make your spacetime as big as your computer allows, which is a large radius, compute this component of the Riemann tensor at different separations, see if you can take the limit, and that is your gravitational wave signal, which you could analyze for observations. Okay? All right. So let's just review some of these key ideas just again. So radiation, in some sense, be it electromagnetic or gravitational, it lives at this in this asymptotic region, null infinity, And actually, we can show that if we take the appropriate limit in this compactified manifold, if we have world lines of increasingly distant observers, just moving out further, 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 then they converge. And I apologize for my somewhat technical language here, but maybe some of you that have looked more into GR appreciate it. There's this null surface here at infinite separation, which we called null infinity or scry, because it's in the future. It's usually called scry plus. Since it's a null surface, it's generated by null geodesics, okay? And these null geodesics at infinity, they correspond precisely to the world lines of observers, of inertial observers, which are further and further out, okay? And there's a natural time coordinate here, which is just the proper time of these asymptotic inertial observers. Now, there's another thing that's important to realize is that what would happen if we just say, okay, things are only well defined at infinity, so let's just go out to infinity and let's just we take our spatial grid points, and we just map them to a finite space, and so we just compactify in space. Okay. Now, what would happen, right? If we have some wave signal, let's just do that here. Right. So now we have chosen a grid where here we have r is equal to 0, and here we have r is equal to 1, but actually this corresponds to physical, but physical r is equal to infinity. Okay? And now we start with some wave signal which now travels outward. Okay? Can that wave signal ever reach this point? No, because the waves travel at a finite speed, at the speed of light, so they never reach here, right? So a little bit later, our wave is maybe here, I don't know, and a little bit later, but it can never reach. So what has to happen? This wave it has to freeze in at some point, right? It has to bunch up a bit, and the closer it goes, it has to become like higher and higher frequency. Okay, so obviously that can't really work because space like infinity is something is not really physical. You can never go to space like infinity. It takes you an infinite amount of time, and you can't really resolve this on a computer. Whereas if you go to null infinity along a light ray, right? If you sit here, the astronomer observes this photon. You're just directly and just looking into the space-time, and you're directly in phase with whatever happens here at the source. Since you're like directly in phase, you don't have this kind of bunching up on frequency shift, blue shift effect, but you have a nicely defined gravitational wave signal up here. All right. So this is just this in very, very brief terms, this basic geometric picture of what kind of space-time we think of when we talk about an isolated system like a black hole or two neutron stars which spiral in here, and then the waves, they really go out to this asymptotic region. And even if we work at with a finite grid, with finite separation, what we really do is construct an approximation of what happens at infinity. Okay? Just to if we talk about infinity and we talk about observations, it's good to put in some real scales, right? So I don't know if let's say we have here a system of two neutron stars, right? Two neutron stars. A neutron star has a mass of about 1.5 solar masses. Schwarzschild radius of the sun is about 3 kilometers. So that's a bit more, 4 or 5 kilometers. That's the basic scale of the source. And then we observe this at dozens or maybe hundreds of megaparsec away. You can convert megaparsecs to kilometers, and you see that really for all practical purposes, we really observe things at infinity. Right? Also, the gravitational wave signal itself here, the deviation from Minkowski metric is extremely small. The typical amplitude of gravitational waves, which we hope to observe, is like 10 to the minus 22 or smaller, okay? So we're perfectly in the regime where we just have waves traveling on a Minkowski background, and really everything, all these calculations of what happens to a gravitational wave within a gravitational wave detector, for example, this is completely well described by just this limiting null surface out here at infinity, which just represents Minkowski space. All right, another thing to mention, but where one can skip the details, is as with electromagnetic radiation, it's convenient to decompose waves into spherical harmonics because gravitational waves are variations in the metric and not in a vector field like the electric or the magnetic field. These spherical harmonics are defined a little bit differently. They are called tensor spherical harmonics. Well, tensor because the metric is a tensor, or more fancy mathematical spin-weighted S equals -2 spherical harmonics, which means nothing else that they use to describe an object like a gravitational perturbation. And then usually what we do is we just and if you see somebody talk about a gravitational wave signal, then usually what they do is either, well, what does it look like, a gravitational wave signal? Well, it's a function of time, and it has an amplitude which somehow corresponds to the metric.
So why is it not S2, not S minus 2?
Why is it S minus 2 and not S plus 2?
It's a convention. It could be S plus 2, right? It's just why is this? Why it's the convention of whether a binary rotates clockwise or anti-clockwise somehow. Whoa.
This corresponds to clockwise?
I'm not sure. I don't know. I think it corresponds to anti-clockwise. Right hand. I think it's just a right. That's it. This is the right hand rule, and so it's anti-clockwise. That's the thing. Yeah. What I want to say. Right. So what does a gravitational wave signal look like? Well, for me it looks like that. And then it becomes very big and then becomes small again because I'm interested in this last part where the things merge together and then ring down. Post-Newtonian people, they're more interested in looking at thousands of cycles before, and I can only count to 5, so just look at the last few. And so this could be the signal in the detector, but if you just if you want to describe these sources, you're not yet thinking about the detector, then what this usually corresponds to is to some spherical harmonic mode, let's say some mode HLM. What's the dominant ones? Well, in electromagnetic theory, the dominant one is the dipole mode. In gravity, we don't have a dipole. It starts with a quadrupole. So the leading order one would be H, L equal 2, and M equals either plus or minus 2. And then there are higher ones, higher corrections. All right. So this is how we usually describe our gravitational wave signal. So if you see some waveform, then it's either detector output or some spherical harmonic component. The total waveform, of course, is a function on the celestial sphere. So a source will create a different signal in each direction in the sky. So the total, will have something like psi 4 as a function of theta and phi. But actually we describe it with this kind of harmonic modes, which are LMs. All right. Just to, you see some gravitational wave literature, or you see some paper about people have evolved binary black holes, binary neutron stars. They computed the wave signal. These are the quantities which they actually compute. Okay. Now, something that we cannot directly observe in the detector, but that's interesting to compute, are also quantities like the radiated energy, the radiated linear momentum, the radiated angular momentum. Here, I just wrote down the z component. And then these are defined in terms of certain integrals. Let's just look at one of them. The radiated energy, for example, would be, so we have to take a limit. Separation goes to infinity in the way that we talked about it before. We have to integrate. What does it mean? Integrate over omega means integrate over the angles, right? The angles in the sky. At that separation, there is an appropriate prefactor. And then we have to compute this quantity psi 4 over all times up to the final time, and energy is something like this quantity integrated squared. Okay? Of course, so this quantity goes to 0 as we move further and further away, right? And so the radiated energy has to be something finite, so it has to be weighted with r squared, because this thing falls off like 1 over r. Right. And then we have similar definitions for the radiated linear momentum or the radiated angular momentum. Right, right here, so at finite extraction radius, we need to perform double Richardson extrapolation in extraction radius and grid spacing. So in order to compute our final answer for the gravitational wave signal, we have to do a double convergence test in some sense, not just in the grid spacing, but also in how far out we extract our signal. And this should be something like at least the order of 1 wavelength, right? Okay, let me just skip that here. And now let's just talk a little bit about black holes. So we've very, very briefly introduced this concept of a Penrose diagram. So now we can make a simple graph of the whole space-time going out to infinity. It's not hard to derive this, for example, for the Schwarzschild space-time. So what would we get for the Schwarzschild space-time? We get this. So who has seen a Penrose diagram of the Schwarzschild space-time? Quite a few. All right. So I think if you haven't seen it before, I think some of the basic features you can still understand. There is a horizon here. Actually, there are several, because there are several null surfaces. The horizon is where you all know the Schwarzschild metric, so this is where the aerial radius is equal to 2m. And this is obviously, we have coordinates where light rays go at 45 degrees. So if you go at for example, you're here, you go at a time-like curve, you just fall inside of the black hole, you end up in the singularity. If you go on a null curve, you go here, you go into the singularity at r equals 0, right? If you want to, so if you're out here, you can escape to infinity, but if you're inside here, you cannot, right? So this is infinite distance, this is null infinity, this is where you can observe something from far away, and this is the region where you can go to infinity, when you can escape, and this is the region where you cannot, right? Here, you always have to go to r equals 0, you have to fall into the singularity. So, an appropriate name for this region is the black hole, because you can't get out. That's the limiting surface, so we call that the horizon, and that's the region where we are, right, where you can get out. It turns out the Schwarzschild space-time has, because of its time symmetry and other symmetries, it has strange features. So there's also something which looks like the black hole region, but it's in the past, just turned upside down. It's a funny region where you can get out, but you can't get in. But if I'm here, I can't get in. I have to fall up here. So since it's a region where you can only get out but not in, and it's just a time reverse of a black hole, this region is called a white hole. And then there's a mirror universe of where we are inside here, and that's it's just like a mirror universe. However, all these features here, they come because we have assumed time symmetry, but astrophysical black holes, of course, they're not time symmetric. They have been produced at some point by there's some collapse of gas, and dust has collapsed from the star, and this has further collapsed and formed a black hole. So they're not time symmetric, and this means that all these regions are not really there. So an astrophysical black hole will have this region and this region only, like it's sketched here. Fine. So what is, oops, sorry for this accident here. So what's we said this is the horizon. It's a null surface, and is also commonly known as the event horizon. Right? We can see in this picture how it's defined. It's a null surface. It's just like a causal boundary. It just goes from infinity. In this case, it's future time-like infinity. Right? All time-like. Where do time-like curves go? All time-like curves, they go up to this point, this kind of infinite point. So from this point, we just take a null surface backward in time. That is exactly the boundary between being able to escape to infinity or having to fall inside the black hole. And this is what we call the event horizon. Then actually the different notions of horizons, and this specific definition is an event horizon. Now, this has a very, very strange, it has a simple explanation, but it's also very, very strange, because in order to find this surface, right, if you're here in the space-time and want to know, am I inside the event horizon or outside? Well, you can't know that locally in time. If you want to know, you have to evolve the space-time to the end, to infinity, and then you can just go backward in time and see whether you're inside or outside. Because the event horizon is a statement whether in your complete future you have to fall in, you can't get out. And you only know this answer if you have the complete future. Very simple. Now, obviously in a numerical construction, computer time restrictions will not allow you to go to the infinite future. Okay, you have to stop somewhere. So let's say in practice you just only can go to here. So this is some restriction in actually computing an event horizon in a numerical simulation. In fact, you can still do quite a good approximation. You wait until things have more or less settled down, until you have formed your final black hole, and then you say, nothing's happening anymore, so I'm in some sense close enough to this point, and now I just do a prescription which is trace back in time and I find my event horizon. But also, the event horizon doesn't help you very much to understand what's happening in the space-time at a certain time because of this funny way in which it's defined backward in time. In order to get around that, well, here we have some of these nice pictures of event horizons. But in order to get around that, there's another concept, which is a so-called apparent horizon, and this definition is local in time. Now let's try to understand what that is, because this is the quantity that we have to compute all the time. So if you want to read a paper about numerical relativity, black holes or neutron stars that eventually form a black hole, how do they know? How do they know they start with something which is a black hole? How do they know that at the end they form a black hole? Well, what they do is they look at the event horizons. And in order to understand event horizons, we have to understand the concept of a trapped surface. Now, actually, I think that this can't be seen very well. But what is the basic idea of a black hole, of an horizon? Sometimes the light cones are tipping over, right? The light cones are not like in Minkowski space, but they're just tipping over, so that there's a surface where the light cone points completely inward, right? That's the basic idea of a event horizon. If you go back to our previous picture here, right? Here, if you locally draw the light cone here, the light cone has kind of tipped inward. Right? That's the crucial feature of the horizon. And there is a way to somehow define this locally in time. A trapped surface, it's a space-like surface, a two surface, like a sphere, and it has the following property that the ingoing and the outgoing wavefronts decrease in area. What does it mean? Imagine you have a sphere, and on this sphere you have some light bulbs, many of them, and you just flash these light bulbs. Then you have like a wavefront which travels outward from the sphere, okay, and another one which travels inward. Usually what's going to happen is that the area in flat space, the area of the outgoing wavefront increases and the area of the ingoing wavefront decreases. Right? It's clear. But if you have a black hole, then the photons cannot escape. They just have to fall backward. So the area of the outgoing wavefront, it cannot increase because they are falling back. So that's the key feature. And so a surface which has this feature that the outgoing wavefront also cannot increase, this is what's called a trapped surface because the photons can't get away. Okay? So this is what somehow locally characterizes this feature of the light cones are just tipping over. Now, we can look at a limiting surface, we can look at surfaces which are just marginally trapped. So which means like inside you're trapped, but outside you're not trapped. And you could have different layers of them. In principle, you could have different layers of them. You could you have some marginal trapped surface, but you're trapped inside, but here not. But in principle, you could have another one around here, okay? Because things have saddle points and other complications. And now, for physical purposes, for observers, what matters is like the outermost surface, right? And so then outside of the outermost ones, things are normal, like in flat space. So we want to look at these just marginally trapped surfaces, and then at the outermost one, and this is what is called the apparent horizon. This condenses the properties of the event horizon into a definition which is local in time. Okay? And this is what you can therefore determine at every single time step. Let's
some light rays and trace its evolution that are using to find this apparent horizon?
No, this is what you have to do for the event horizon. For the event horizon, you would have to do exactly what follows this Penrose diagram. Go to the future significantly, and then just trace light rays backward in time. Okay, but it turns out that for the apparent horizon, because it's like a local property, you can write down an equation which is local in time. Actually, I wrote it down here. You can define quantities which are usually called the expansions. Well, what does it mean, expansion? Expansion is just the rate of change of the area of the wavefront. Okay, and there's one that goes out and one goes in, so they have two versions with two signs, and then essentially just doing exactly the calculation which Thomas has done for you, the 3 plus 1 decomposition, but now you do a 2 plus 1 decomposition because you have your 3-dimensional space. In the 3-dimensional space, you consider some kind of spherical object embedded there, okay? And now you make statements about what's the local property of waves propagating away from there, and you do it with so we write they're not in like a 3 plus 1, but just in a 2 plus 1. So 2 plus 1 decomposition, using exactly the same formalism that you have learned, and then you can express these expansions in this form. This is the extrinsic curvature of the 3-dimensional hypersurface, the same thing that appears in the ADM equations. This is the trace, and RA is just the space-like unit vector, right? RA is 1. So this takes the role of what so far you called NA, the time-like unit vector. So you remember this epsilon that Thomas had. Now you do it -1, do exactly the same formalism, and you can derive this equation. And it turns out that this is an elliptic equation, so it has a character somehow like the Laplace or the Poisson equation. It's nonlinear, it's a bit complicated, and you can just solve this at every time step and find this surface. Okay? You can also, this surface, you can associate properties with it. For example, you can associate a mass with it or an angular momentum, and so you can, finding these surfaces, you can analyze the physics of a black hole at a certain time. So, for example, what does it mean to have a space-time with 2 black holes? It means that you have 2 separated apparent horizons. What does it mean that the black holes have merged? It means now you just have a single one, a single outermost marginally trapped surface in our technical language. Remember these characteristic speeds which we defined. The characteristics, so now at an apparent horizon, right, the characteristic, the light cone tips inward. So it means all the information flows inside. We could write this in terms of our characteristic variables, and the technical term that is used very often is to say that the apparent horizon is an outflow boundary. All the information flows out of the computational domain. We have just discussed before that we can only put boundary conditions on inflowing information. So if you could just cut a hole where the apparent horizon is, we don't have to put any boundary conditions. In fact, we're not allowed to put any boundary conditions. Okay, so we don't actually have to evolve what's inside, because we just cut it out, and because everything goes inside, we don't have to worry. Why would we want to do that? Well, there are the very well-known singularity theorems of Penrose and Hawking that show that under very, very general conditions, if you do have a trapped surface, you will form a space-time singularity in the future. For this reason, we know that inside of a black hole, inside of a horizon, you have a singularity. Now, computer codes don't like singularities very much, so one way of dealing with this is to just cut out the inside of the apparent horizon. We don't have to put boundary conditions. And this way of doing things is called black hole excision, because it just excites what is inside. It turns out that the idea is very simple. In practice, it's a bit complicated, and so there are also other methods to deal with it. But it's a good thing to know what's the basic idea here.
Do you know that the event horizon is always inside the apparent horizon?
No, the apparent horizon is inside of the event horizon, right? So under very general conditions that you don't have naked singularities and other strange things, the apparent horizon is inside of the event horizon. As long as if you're in a situation where the black hole is essentially time independent, then they'll coincide. All right. Now, right, half an hour more, right? Yeah. Okay.
Yes.
So we have seen already. So now we've seen two things. 2 points about general simulations of astrophysical objects. What's going on with waves? How to compute them? How to connect them with the asymptotic structure of the space-time? How to locate black holes? Locating black holes is also important, for example, when you want to construct initial data for black holes. When you want to solve the constraint equations, because you have to know where these objects are, in your grid. Okay, how to characterize their properties. Let's talk a little bit now. Let's move over somehow that we have understood these concepts to more computational aspects. All right. Let's think about what would we have to do if we extend our code for the wave equation to handle the full Einstein equations, to simulate some compact objects, right? Well, first of all, you need 3 space dimensions. That's, in principle, is somehow not even so complicated, right? You just have to, now you have to take your derivatives in 3 directions. The stencils are a bit more complicated, but it's not a big deal. So it would be quite straightforward in some sense to extend your wave equation code to 3 space-time dimensions, to 3 space dimensions. What do you have to do to deal with the Einstein equations? Well, the Einstein equations are just more complicated versions of the wave equation. They have lots of nonlinear terms on the right-hand side. You code them up, maybe with computer algebra, write them in C and Fortran with computer algebra. But the basic properties of these equations are those of the wave equation. So if you just write down all these nonlinear terms, you can still use your code that you wrote to deal with the Einstein equations. But now we have to think about what's the physics that we want to deal with here. So in general, we will have some compact objects, maybe a single one, maybe a supernova, or maybe 2 compact objects like binary black holes or binary neutron star black holes, something like this. And so these objects, they usually have very different length scales. In the most extreme case, if you have black holes, because black holes are just the most compact objects that you have, right? So you have the individual black holes, which they are very, very small. In fact, if these black holes may have roughly the same size, or they could have a mass ratio. If they have a mass ratio which is significantly different from 1, then again you have very different sizes, because one black hole is much smaller than the other one, which again can create problems. Then you have the scale of the orbits. The orbits are much larger than the black hole. If you do this numerically, you can typically afford to start maybe at a separation of 10 mass units, maybe 15 mass units. You have something between 5 or 15 or so of these orbits. That's what you can afford. So this is much larger than the, let's say, roughly m or 2m wavelength, which is, because we have speed of light, wavelength is about the period. If the period, so if the index of the spherical harmonic is m, then you have to somehow rescale your wavelength with m. You can actually compute at the end of the simulation, you have this ring down, you can compute the frequencies of the ring down, and they are roughly between 10 or 16, 17 m, okay, because we know what they are for different Kerr black holes. We can just use Kepler's law, which we have already used before, to have a rough estimate of how the orbital frequencies relate with the separation. And so we get, for example, at 10 m, the orbital period is about 200 m, right? So that's the fundamental scale of the waves initially, which is much, much larger than this one. So now we have a scale of about 1 m, about 2 m, about 200 m. Then we have to capture, we have talked about asymptotics, so now we also have to capture the fall off of the field going to asymptotic distances. So there are different terms in the metric which fall off like 1 over r to some power, and we have to make them small. We just have to go far enough so that we're essentially Minkowski spacetime. If you want to do this, we have to also go to several hundred mass units in separation. So we see that we have many, many, many different scales, and we can just not capture them, obviously, with a uniform grid. So sometimes we have to change our grid spacing, right? And so how can we do that? Well, we have to use what is called adaptive mesh refinement. Okay, we just have to change, we have to just change the grid spacing in our three-dimensional grid. The easiest way of doing this is you think of you have some boxes. Let's just do it this way. Right, so now we have our two black holes. Here's one black hole, and here's another black hole. They have different masses, so this black hole is a bit bigger. Okay, and so now these black holes are very small. We have to resolve them in the grid. So now let's put a box around this one here, and let's put a box around this one. Okay, and we have to think about how we have to do our grid spacing so that this thing is well resolved. But then these things have to orbit around each other, so we have to do a whole hierarchy of boxes. Here's another one, here's another one. This may get coarser, and we have to make a box around them. This can give a coarser grid spacing. And then we have to make more and more boxes of a hierarchy of boxes, so that this was a scale of like 1 m. So now 10 m is somewhere. Well, I should have put them farther away. Now this is the orbital scale of 10 m, and then we have to go to the wavelength, so 200 m. So another factor of 10 or 20. So now in order to get the waves out, we have to be here. And in order to get the asymptotic fall off of the field, we have to be somewhere in the bathroom. So we have many, 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 many levels of refinement, right? Just having these boxes with different delta x. The bad news is that really makes the code a lot more complicated, because these different boxes, they have to communicate with each other. That creates a lot of overhead. There's also good news that for compact binaries, we don't have to make a very general algorithm, because basically we know where we have to put more resolution, where the objects are, right? So, and if these objects move around each other, we just have to move these boxes with the objects. We know exactly where we have to do this. We just follow these objects. So that makes the algorithm much more simple than the most general thing that you can do. If you have a complicated fluid simulation where lots of things happen, maybe in a supernova, there are shocks and all kinds of structure you don't know in advance where you need the resolution. You have to have some criterion where you say, oh, so here something's happening, I need more resolution here, now I need more resolution here. And then things have gone away, they have damped out, now I can forget these small grids again. So this is very general, it's very complicated. Here we don't have to do this. All right.
So here sort of scales is like maybe a factor of 1,000 different than the sort of black hole scale and the wave scale.
Yeah, on that order, yeah, right.
So in sort of fluid dynamics, etc., is it significantly larger? The turbulence and so on, possibly much larger.
Yeah, it's possibly much larger. The difference is there. So if you don't have a significant gravitational wave amplitude, you don't actually have to go very far. You just more or less you have to go maybe just a little bit further than the surface of this object. And then if you want to get your waves out, you just use the quadrupole formula. You really don't have to go to asymptotic regions. So, but then for the other reasons, you have these very, very large scales. Right? And because in a supernova, this has it's the size of a star, but then the finest structure maybe happens on 100 meters or so, and it's really, really you need these large scales. Okay, now one of the problems is that if you remember the CFL condition, right? The smaller the delta x, the smaller the time step. So you don't just have to choose to change the spatial grid size. You also have to change the time step. So this grid has to evolve faster than this one, and this one has to evolve faster than this one. That's another obvious complication. Not all of the grid points, they update with the same frequency. Or you could, but these ones, they certainly have to update very often. So if all of these hierarchies of grids have to update as often as this one, that's obviously not very efficient. Okay? All right. Let's just skip some of these other points and just very, very briefly think about what happens when different grids update with different frequency. The basic algorithm to do this is called Berger-Oliger mesh refinement. And what's the idea? Well, here we have two grids. That's a fine grid and that's a coarse grid. Usually, just to keep things simple, we'll choose the grid spacing here by a factor of 2 finer, which means that we also have to choose the time step half the size. So when this coarse grid makes 1 time step, this one has to do two time steps, right? That's the basic idea. Now, so what do we have to do now? Because at some point, right, this fine grid here, I need some information when this evolves, right? So the easiest thing that you can do, for example, is that when this one has done like 1 step, this just has not done a step yet, you could just interpolate to this time. Then you have data here. Then you can evolve to this step, and then you are synchronized again, right? The thing is that, so now when you interpolate here, you make a certain error, and you have to worry whether this causes you any trouble. And there is you can, what you can do is you could have some extra points here, which is just like buffer points, okay? You just have more and more, here, in order to compute the finite difference stencil for this point, I need a point here, so I have to just fill in this information. If I would actually have an overlap between the grids, I just have fine grid points all the way up to here. I don't have to fill this in, I just have this information. Okay? And during the updates, well, things eat in here more and more and more. But if I have enough points here, I don't need any time interpolation information, and I can get up the way to here. So we just have some extra points, which we usually call buffer points, for this purpose. You need as many buffer points as is determined by the width of the stencil and how many steps you do here. Right? So for example, Radiated, you have to do 4 of these intermediate steps. Problem is that you want to do things very accurately, so we want to work with a higher stencil, which is wider. So how many buffer points you need? Well, the stencil width times 4 Runge-Kutta steps, but then we do it in 3 dimensions. No, it's not just in 1 dimension, but it's this amount of buffer points left and right to the third power. So there's a lot of extra information that you have to store, and so that can be quite expensive. But the basic idea is relatively simple. And so this is how, in fact, how this is done, how we evolve different boxes with different time steps, and we have extra buffer points to store the information that we need during the time of
Power times 3 left, right?
Sorry?
Why third power?
I mean, if we work in 3 dimensions, right? Now let's think of some astrophysical problem. Everything is in 3 dimensions. There's 3-dimensional boxes, so you have to have your buffer points here and here and here and here and here and here. Right.
For extrapolating that buffer point, we need one step suppose that I have like values at delta t. Suppose we want to go from t to t plus delta t, or there in a mesh point where you have a higher resolution, you need one grid which contains all the data of t plus delta t by 2. This middle line. Okay. So like for extrapolating that buffer point, you need one grid. And you are just taking the data from t plus delta t, but you have not computed that one.
Well, what you can, right, this is a good point, but what you can do is that you update the coarser grids first, then you have that information, and then you go from the coarser grids to the finer grids. You define grids at the end. And then you always have the information that you need. And once you are done with the whole thing, then you just use the information from the fine grids. You always take the information on any given grid point, you take the information from the finest grid, which covers that grid point. But you first update the coarser grids. And then it works out. But it's a good point.
How much is the zones you require? Will it not depend upon the kind of method you are using?
How many buffer zones? How many buffer zones you require? It doesn't depend on the metric. The buffer zones depends on, what's the width of the spatial stencil and how many updates you have here for your Runge-Kutta scheme. What does depend on the metric is, how big you have to make these boxes, how big you have to make them to fit in your neutron star or whatever structure you want to resolve. Okay, that comes from the physical problem. This just comes from the mathematics. Also, just to finish, we talked a lot about finite difference methods because some of these are the basis to understand how things work. But you can do things in other ways. All these other methods, they are related to finite difference methods in some sense, but in practice they can look quite different. One question you can ask is if higher order finite differences, second order, fourth order, and so on, they can give us better accuracy. Now, what's the highest order we can use in a grid? Well, the highest order is that you just use all the grid points in your finite difference stencils, right? And then if you would make your delta x smaller, then you have more points. You use even a higher order, okay? And it turns out this makes perfect sense. And another way to understand this, to formalize this, is what it corresponds to is not to represent your solution by some piecewise local polynomial of a fixed order, but by a polynomial which just goes over the whole grid. And another way to call these functions which extend over the whole grid, we would usually call them a global basis functions. Right, so now we expand not just locally over a few grid points, but we expand the solution that we're looking for into basis functions which just cover the whole grid. And because we think of in a basis function decomposition that covers the whole grid, these kind of methods are usually called spectral methods. So the basic idea is just in order to compute a derivative, we don't just use a few points, we just use the whole grid which we have. if you do something like mesh refinement, then we would have like different bases for the different boxes of different sizes. All right. So a more systematic way of considering this or writing this is that now you're searching for some solutions in some finite dimensional space for some partial differential equation defined by some derivative operator, and then you're looking for the residual error, the residual which you get from just evaluating your differential operator on this truncated function, which just takes the basis expansion up to a certain number of basis components. So we can think of different kinds of functions. So there will be the expansion functions, so the kind of which are called, they're also called trial functions, and then we can just take the solution that we're looking for and just expand it in terms of these expansion functions. And then we look at another family of functions which we call test functions, and these are the ones which are used to which used to test the residual, compute how small is the residual for a given expansion. And then depending on what kind of functions we choose, there are we get different methods. So for example, finite difference methods are those where the trial functions just correspond to overlapping local polynomials, right? Which we have used to derive. Remember, we have explicitly derived our finite difference formula from considering, in the second order case, from considering a second order polynomial. Now, fourth order, we would use a fourth order polynomial. Then there's a method which is called finite element methods, and here the trial functions are some still local smooth functions. Could again be some polynomials of a fixed degree, and then the method which I started to explain, the spectral method. Here the trial function is just some complete global basis. For example, if you want to use a periodic problem with periodic boundary conditions, we could just expand our solution as a Fourier series. That would be the simplest example of right? If we expand our solution not in a local polynomial, but in a Fourier series over the whole domain, that's the simplest example of a spectral method. Right? So for this problem, the wave equation with periodic boundaries, we could just have first expanded our solution into a Fourier series, and then somehow write our equations for the Fourier coefficients. Right? If the solution is not periodic, there's a very standard choice of these basis functions, which are so-called Chebyshev polynomials. I just write them here, mainly just to give you this name. If you're ever tempted to use these spectral methods, there are basically two technical cases. Periodic, you use Fourier series. Not periodic, you use Chebyshev.
Usually in the periodic case, there's an issue of sampling rate. So, I mean, it can become ambiguous if the bit spacing is uniform. So,
you have to run. They're the same basic rules of representing, functions in Fourier space applies, right? We use Fourier space a lot to think about finite difference games. It's the same thing here, and if you have signal at very high frequencies, you get a problem with these aliasing errors, and what you do about it is very similar. Right in the finite difference case, what we have done to get rid of problems of the high frequencies, we have added this, what we call, we have added this dissipation, Kreis-Ohllinger dissipation. Here, since we're working in the Fourier description, we can directly work with the Fourier method, with the Fourier transform, and we just say all the high frequencies in the Fourier transform, just set them to 0. Like at every time step, you pick the highest 10%, the highest 30% of your Fourier frequencies, and just set the signal to 0 in those. And that gets rid of these problems. All right. Then again, so some of the different classifications of these spectral methods, and these work by what you choose for your test function, and the method which is most widely used for the problems that we consider. They are so-called collocation methods or pseudo-spectral methods, where your test functions are actually delta functions. So delta functions at your grid points, which are also called the collocation points. And so the idea is that for these methods you both use the spectral grid and the physical space grid, okay? And whenever you compute a derivative, you compute a derivative in the spectral representation. And whenever you compute like a source term, you do that by evaluating your source on these collocation points, like on your grid points. Okay? For example, if you want your source term is some nonlinear term where you have to take the square of the solution. Taking the square of the solution in Fourier space is actually quite expensive because there's no square of all these Fourier expansion terms. So if you want to take the square, you just at every grid point you just compute locally the square. Okay? But if you want to take a derivative, you just taking a derivative in Fourier space is just multiplication by I omega. So you go to Fourier space, you multiply every Fourier mode with I omega, and you transform back. That is a procedure which can be done fast, and it's very accurate because you take into account all the information from all the basis functions. And if you add more grid points, this corresponds to having a higher order, and it gets more accurate. And where for the finite difference methods we had some kind of polynomial convergence, so the error goes down like a power of delta x. Here, asymptotically, it decreases exponentially. There are other methods as well, other methods which use different kinds of test functions, but I just put them here for completeness, because at least for our purposes, they are used less in practice. They are more complicated, and right now, the pseudospectral method is very well used. It's sometimes used for the time evolution problem, and is almost always used to solve elliptic problems. Why? Because if you have a time evolution problem, you can create more structure. You have a lake, you throw in a stone, you have more and more structure in time. But an elliptic problem is like an equilibrium problem, right? They tend to have very smooth solutions, and then it makes more sense to have this expansion in many, many, many basis coefficients, which corresponds to using these kind of methods. I think we're basically running out of time. I don't want really to talk much about these technical things. For completeness, I want to raise, there's a different method which is very, very well used, which is finite element methods. Here you just compose your solution of these different finite element methods, and this is very, very flexible if you want to adapt to different domains, to complicated domains like what you have in engineering. So if you're an engineer, okay, then there are probably no other numerical methods apart from finite element methods, okay, because you are using very, very complicated domains. You may not be interested in the ultimate precision, but you have to adopt to very complicated domains. And so the best method for that is finite elements. So if you're quitting GR and you go into engineering, it's this slide is what you have to remember. Okay. There are also there's another class of methods which are called finite volume methods, and I'm not going to say anything about those. They are using special conservation properties of the solution, and they are useful when you have non-smooth solutions, when you have distributional solutions. When you have distributions, right, you can't multiply distributions, for example. Distributions always are defined, operations on distributions are defined in some kind of integral sense. So to some degree, what you want to do is you want to redefine your numerical algorithms in terms of integrals. You don't think of it as, taking different grid points and taking differences and so on, but you think of them as taking the integral over some computational cell. That's why they're called finite volume methods. They're useful for non-smooth solutions, like for fluids, and David next week is going to tell you all about them. We have occasionally talked a little bit, made some hints about actual hardware. Just when we talked about double precision, there's some relation with what's the actual hardware that you're using in your computer. There's a kind of a newish development, so-called general purpose computing on graphics processing units. What is that? It's also something to be aware of. Modern computers, they will have a central processing unit, a CPU. They will also have a graphics processor to quickly render three-dimensional and two-dimensional graphics. And these are optimized to basically do numerical calculations on like graphics objects very, very fast. Right? In particular, for example, for games. Okay. Now, it turns out that these things have very much advanced, and to some degree they can be used for general purpose calculations like solving computing a Fourier transform, or maybe even solving a partial differential equation, essentially on the graphics card. And you can get graphics cards which are just really optimized for that kind of purposes. Graphics cards have many processors. Each of these processors is somehow weak with very small memory, but you can have hundreds of thousands in a small card. Okay? So for operations which somehow vectorize very, very easily, this is very useful. They're difficult to program basically because each of these processors just has little memory, so you have to be careful with the transfer of memory. And since if you have a problem which parallelizes into many different tasks, hundreds of thousands, the logic also becomes more complicated. And this is not useful for all kinds of problems that you have, but if you have a problem which fits with this kind of architecture, one can benefit a lot from that. Now I think I'm basically run over time and I have not much more to say, so I would say let's just stop here. Let's see if there's anything else that I want to say. Not really. All right, thank you. And now what we're actually going to do is we'll look for Thomas, and if he's not around or not well, then we just do the exercises now, and then we look again whether he has appeared for lunch, and then we think about what to do.
But this sort of formally finishes the first course, and let's thank Professor Husa for
So I'm around. So I'm around actually the whole next week.
Yeah.
So whatever questions you have, but coding up David's finite volume method still leaves you time to finish the other things. I'm happy to help and answer questions. I may help Mark with his lab exercises next week, so I'll be around for discussions and questions.
I guess next course by Mark will be sort of a logical continuation.
Right, exactly, right.
We'll be back at 11:30.